So welcome everybody, thanks for coming. Good afternoon, hope lunch was satisfying in some capacity. Talk this afternoon is Escape Velocity, better metrics for agile teams. I think in the brochure it might say better metrics for software teams. This is actually based on a book that I've written, and the subtitle of the book is in fact better metrics for agile teams, so that's what I went with here. I'm Doc Norton. I work with Enbelay, which is a consultancy in the United States. We do process and leadership coaching for companies that deliver software. You can find me anywhere as Doc on Dev. All the things whack Doc on Dev, that's me, including Twitter. So escape velocity. Now I'm going to do something here. I don't normally do this in talks. It's a bit of an experiment, but I want to see if we can actually make this work. So I'm actually going to ask everyone to stand up for a little bit here. And I will give you instructions on when you sit, okay? Okay. So, we're talking about metrics, but we're going to start with velocity. If you do not measure velocity at all, please sit down for your teams. Okay. If you do measure velocity, you're standing up. If you have a low confidence in your velocity. In other words, it might be 3 one iteration and 27 the next, or something along those lines. Please sit down. Okay. If you do not have a direct correlation between velocity and release, in other words, you're measuring velocity every week, every 2 weeks, but you release every 3 months or every 6 months, then please do sit down. Okay. If it is difficult using velocity alone to predict when a feature or batch of functionality will actually make it to production, please sit down. We've got 2 folks standing. If, in order to get this good at predictability, you used metrics other than velocity, please sit down. Got 1 person standing. My fundamental premise is that velocity is useless. Nearly useless. For most teams, velocity isn't stable enough to be reliable. For those teams where it actually is stable, it's often disconnected from actual deployment or delivery. For those where it's not disconnected, they still tend to use other metrics to actually help them get better at delivery. Velocity itself turns out to be not a particularly useful metric. So why is it that velocity is nearly useless? And I figured to figure this out, why don't we start with what is velocity? So what is velocity? Does anyone have kind of a when I say velocity, what do you think of? Speed? Speed. All right, that's fair enough. Usual definition is something related to work units over time. Story points per sprint, ideal days per iteration, whatever it might be, right? Standard definition of velocity is work units over time. Those of you that know even just a little bit about science, physics, realize that can't be velocity. It doesn't have a vector. That is merely speed. So it's work units over time towards the delivery of value. It now has a vector. It is now actually velocity. Fantastic. But what else is it? Well, it turns out that velocity is also a lagging indicator. So it tells us what happened. It tells us something about what happened in our prior iteration or iterations. Now here's the thing about lagging indicators. they're actually not good short-term predictors. They're decent long-term predictors. You can look at them over longer cycles, and you can use them to make certain assumptions about things. For example, we know typically in retail that sales is going to go up around the end of the year, every year. But we don't really know how much, right? We just know that it's going to do that because in a long-term cycle, that's what it continually does. I overheard this discussion the other day. Somebody was talking about potential for climate change, and I don't know what your stance is on that, but I thought that their perspective was interesting. They said, you can't trust these people, these climatologists, meteorologists, all of these folks. They can't be trusted. They claim that they know climate trends, but they can't tell you what the weather's going to be tomorrow. Same kind of thing, right? I'm showing an unemployment line. Unemployment is a lagging indicator. If the unemployment rate is rising, it is because the economy has been sagging. Economy sags, unemployment goes up. It's a lagging indicator. What else is velocity? What happens to be the measure of a very complex system? We've got all kinds of inputs, we've got all kinds of outputs, we have all sorts of processes. There's a bunch of different things, interactions that are happening here. And then at the very end of that, some number comes out, and we look at it and go, number good, or number not good. So I got to think about this, lagging indicator of a complex system. What are other things that we know about that are lagging indicators of complex systems? Something that maybe we could use as a metaphor, maybe something that we're all familiar with, that we all share. I thought, well, your body weight. Your body weight's a lagging indicator of a complex system. You certainly have inputs and outputs. There's all kinds of activities that take place. And at some point you step on a scale and number. Number good, number bad. If you think about your body weight, what are things that might affect your body weight? Christmas, clearly. Diet, exercise, genetics, physical health, mental health, your environment, the work that you do, stress levels, your social network. These are all things that might actually affect your body weight. Does any given body weight, as a number by itself, mean that a person is healthy? No, it doesn't. So if we think about that, does any given velocity mean that a team is healthy? No, it can't. It's not enough information. Now, going along with this metaphor, how might someone lose weight? If I decided that I really want to shed a few pounds, maybe I want to lose 10 pounds, 5 kilos. How might I go about doing that? What are some things that I could do? I could eat less. Thank you. Could exercise more. I missed this one. Cut off a leg. Well, there you go. Live outside during the winter. Freeze. Sauna. So this gentleman made a very good point. This one I think made somewhat of the same point. There's a lot of things you can do to reduce body weight. Some of them may provide an improvement in health to the overall system, but others may not. You could cut off a leg. You could smoke crack. You could consume nothing but amphetamines. And you would hit that target. You would hit that goal. You would achieve that weight. But you would not improve the overall health of the system. Same thing is true with velocity. How might a team increase their velocity? Anyone done this? Increase your estimates. velocity goes up. It's like magic. You could limit your WIP, right? You could reduce your batch size. You could reduce dependencies. There's a number of things that you could do. But you could also increase your estimates, skip testing, cut corners on internal quality. You could work more hours per week. You could increase your work hours from 40 to 80. Your velocity is probably going to go up. Not by as much as you think, but it probably would. And of course, you could increase all estimates. Same point. There are things that we can do that would improve our velocity, but not necessarily create an improvement in health in the overall system. Now, I see this a lot. Good intentions or not, at some point, someone in a position of authority asks a team to please move a little bit faster. Hey guys, I've been looking. I ran a burn down. And it shows that we're going to miss the deadline by like 2 weeks. Now, your velocity's been 17. If you could just get it up to 24, we'll make the deadline. What do you say? Can you do that for me? Even with good intentions, what ends up happening here is a couple of things. One, we've invoked this thing that's called Goodhart's Law. Goodhart's Law is from economics, and it states that any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. Right. What it means is if you take a metric, a lagging indicator especially, and you set a target for it, that metric instantly no longer means what it once meant, and the target no longer means what you think it does. And the odds are what you've done is you have created what is referred to as a perverse incentive. These happen a lot. It's an unintended result, typically contrary to the interest or intent of the incentive. So we can see here in this case, we wanted to get call times down. Why do we want to get call times down? Probably so that we could serve more customers. Why do we want to serve more customers? To have more happy customers. What happened? Call times went down. Customers probably aren't very happy. This happens if we set a target for velocity. Estimates go up. Quality goes down. It wasn't our intent to have those things happen. But when we set this target, that's what happens. Now, something that's interesting for me is very often I will hear managers say, you know, man, them employees, they gamed the system. They gamed the system. I gave them a goal, and then they mucked around and gamed the system in order to be able to hit that goal. I want to get something straight right now. It is not the employees that game the system. Managers game the system when they set goals for measures. The rest is natural consequence. You set up a system that incentivized these specific behaviors. You got these behaviors. Think more deeply about your systems. All right. So we've established a bit that velocity maybe is not a very good goal, or not very good metric, certainly not good to set goals for velocity or any of these types of metrics, but it's not really what we're here for. We're here for better metrics, right? So let's take a look at variable velocity, because this seems to be one of the main causes. Folks have a difficult time with velocity because it's all over the place. Now, if you took a look at this chart right here, this is a team's velocity over the last 10 iterations. Looking at this chart, what can you tell me about this team, their behavior, their motivations? What challenges are they having? You can't tell me anything, can you? You could take a bunch of guesses. You can make some assumptions. You can decide that all developers are lazy, so it must be this. Or you can decide that all product managers are difficult, so it must be that. But you don't actually know what the challenge is here at all, right? So typically what we would do is we'd set some kind of a goal for these folks to stabilize this velocity or to hit a certain rate. Now, Deming tells us, don't do that. Setting quantitative goals doesn't actually matter. Fix the methods that underline those goals. So if we're going to fix the methods that underline these goals, if we're going to actually look at how do we correct our velocity, get it stabilized, what are some common causes? One, deferred maintenance. This is probably one of the ones that is overlooked the most, in my opinion. Right? No time to clean the code, no time to refactor, no time to upgrade the infrastructure, deliver, 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 deliver. What ends up happening is these all gum up the system. They cause it to move slower and slower and slower, all in the name of speed. What else? Well, another big one, actually, is batch size. Now, this can come from variable story sizes, or this can come from consistently large stories. Either of those might actually lend to variable velocity. But the bigger the batch size, the greater the risk. Now, when I say batch size, it's be referring to a few different things. This might be the size of the stories. This might be the length of the iteration. This might be the size of the release. And that might be, it's actually all of those things. Longer iterations, bigger batch. Larger stories, bigger batches. Larger releases, bigger batches. The bigger the batch, the greater the risk. There's more surface area, if you will. There are more changes that are happening at once. There is more potential inside of that for something bad or catastrophic to happen. The greater the risk, the more planning that is required. The more planning that's required, the more time it takes. The more time it takes, the bigger the batch gets. It's a vicious cycle. What else? Well, it turns out work in progress is a huge contributor to variable velocity. The more we have in flight at any given time, the harder it is to get this stuff done. So there's a mantra: stop starting, start finishing. Don't start another piece of work until the one you're on is actually completed. If it's blocked, spend the energy on removing the block rather than doing the easy thing and picking up yet another piece of work. So these are kind of three key causes of poor velocity, variable velocity. There's clearly others, but these kind of come out on top in most companies that I've seen, most teams I've worked with. So, metrics. We want something better, right? So let's look at that. Better metrics for deferred maintenance. Well, velocity clearly doesn't tell us much about that at all. So what might we want to look at? Code complexity is the thing that we can relatively easily look at. I get some arguments from folks around this one, but it's pretty straightforward. Complexity, there's a few different ways that we can measure this. There's cyclomatic complexity, known as McCabe's number. There's ABC complexity. Fundamentally, all these things are measures of branches, assignments, that type of stuff that's in the code. Cyclomatic complexity is just logic branches. You go, okay, what difference does that make? Well, it turns out that there's actually a direct correlation between complexity and defects. So let's take a look at this. What does this actually look like? So if we look at code complexity, a straight linear program, no conditionals in it whatsoever, typically has a complexity of 1. Do, until, while, and for all have complexity of 2. And a case statement grows in complexity by 1 for every new option that's added to it. So it grows by 1. If that case statement also includes exits from the program, so there's not a single exit, then it grows by 2 for every new option. Like I said, the reason we care about this is there's a positive correlation between code complexity and defects. The more logic branches we have, the more likely we have defects. I can't tell you that if you have a cyclomatic complexity of 24, you will find 3 defects in production. But I can tell you the higher the complexity, the more defects. Complexity is relatively easy to fix. We can look at things like polymorphism to actually flatten conditionals. It really comes down to well-composed code has lower complexity within each of the methods. So complexity is a good one to take a look at. Another one, I think kind of obvious one, is escaped defects. Now the thing with escape defects, so here what this is these are defects that have actually made it into production. So if you found it in UAT or QA or whatever else you label your not yet production environments, it's not a defect. That's a part of your process. You put those environments in place so that things don't get out into production. But once it's in production, if it's found, that is an escape defect. And what we simply do here is we could, and many teams do this, simply log the count of defects per release, per iteration, whatever you want to do, right? Challenge with this is that it can be a little bit misleading. You may find situations where your escape defect count is creeping upwards and you think, uh-oh, this is really bad. And it is not a good thing, right? But it might be related to your throughput. If your throughput is also increasing, in fact, increasing at a rate significantly greater than your defect count, then maybe it's not as bad as you think. So what I typically do is I also take a look at throughput, which, by the way, is just another word for velocity. And then I just combine them. So you look at a percentage of defects by throughput. How much did we deliver in this iteration, and how many escape defects were a result of that delivery as a percentage? And then you have a better set of sense of trending. So these are a couple of ways that we can look at deferred maintenance defects in code. We talked about some other root causes. Batch size. So batch size, this is a little hard to measure because, as I mentioned, it's story size, it's iteration length, it's release size, right? It's a bunch of different things. And if we said, oh, well, let's just use story sizing to indicate batch sizing, well, I can make all my batches smaller. Everything that was a 5 is now a 3. Everything that was a 3 is now a 2. Everything that was a 2 is now a 1. Right? I can instantaneously decrease my batch size if I do that. So what else might we use that's actually a little more telling for us? One of the things we take a look at is release frequency. Assuming all other things equal in your system, the more often you release, the necessarily smaller that release must be. So as your release frequency increases, your batch size is very likely decreasing. Again, all other things, equal. If it turns out that you're adding staff to the team on a consistent basis, maybe your release frequency is going up because you've got higher capacity and the releases are still the same size. But small releases beat big releases just about every time. With small releases, we get a bunch of other benefits. We've got optionality, flexibility, we learn faster, and we actually have more safety with small releases. Now, a lot of organizations don't want to release in small batches because if the users see anything that isn't 100% done and polished, they will run screaming and never, ever, ever, ever come back. I've not found one organization that I've worked with or that any coach I know that's worked with where that's actually been a truth. The reality is we do the small releases, everything is just fine. And because we have a smaller surface area and we have smaller impact, we actually have much lower risk. It's actually safer to do it this way. All right, what else might we look at as a metric for batch size? This one's a little weird. Coupling. Now, coupling, if you were in a talk earlier, you recognize this diagram. This is basically the number of lines between methods in a system. The more connections between them, the worse it is. The more tightly coupled the code, the more places you need to make changes every time new functionality is introduced. Right? And the more places you need to make changes, obviously the larger the batch size. So if my intent is just to change this one little thing in the application, but when I change that, it means that, oh, gee, I changed the employee and now I got to change payroll. I changed payroll, now I got to change, accounting. I changed accounting, now I got to change. Right? That will automatically increase our batch sizes. So a lot of systems, when you first look at them, they've got a lot of high coupling. Here we've got two things. I don't care what these things are. These might be your shopping cart and your cash register. These might be your employee and your payroll. It doesn't really matter to me. You've got two things in your system. We can take a look at these and we can see that they seem to know a lot about each other. There's a bunch of connection points that go back and forth between them. Also, there's a lot of chatter inside of them, which probably indicates things to me like the item knows how it is priced or other such oddities like that. So we can pretty easily reduce the coupling. We can do things like, one, create some kind of an API or separation so that these two things talk to each other through this one connection point. Now, internal changes to either one are safe, and then we can go from there and start actually decoupling the internal pieces of those. And now what we've got is not only low coupling, but high cohesion. High cohesion is where the things in a method class area are all very closely related to one another. And things that maybe they talk to every once in a while are over here someplace else. This code structured in this way, and obviously I'm just using some simple objects to represent this, is much, much easier to change. I can change one place, not worry about all of the other things having to be affected, and I can release just that one small thing. All right, what's the other one? So we had work in progress, right? Stop, starting, start, finishing. How do we measure work in progress? Now, an easy enough way to do this is just to look at almost any tool you have these days. If you're using any kind of electronic tool, will show you how much work in progress you have. If you're using a Kanban board that's on the wall, you can literally look at it. How many cards are in this lane? Set a whip limit for a lane. Are we exceeding the limit? Why are we? Talk about it, right? Why do we want to do this? So let's take a look at the impact here. So let's say you have 4 tasks of 8 hours each. It's the beginning of the iteration. These are all front-end tasks, and you are the only front-end developer on the team. Now, I've just articulated a series of problems with your team, but that's all right. You need to get these done. 4 tasks, 8 hours each. How long will it take you to complete these tasks? 4 times 8 is 32. 32 hours. Yeah. So, beginning of the iteration, they're all important. You've got to get them all done. Go. You start them all at once. Is this what it looks like? You slice your time. Boom, 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 boom. 32 hours has passed. It's done. No, it's not what it looks like. I see people shaking their heads. Why not? This should work, right? What was that? Context switching. Ugh. Yeah. So it turns out that context switching has a cost. Studies have shown that that cost is roughly 20% per item, compounded. So that 32 hours worth of work, when we slice it up this way because they're all important and we got to get them all done, actually takes us 48.75 hours to complete. You can see most of the time ends up being spent in context switching, or a great deal of the time ends up being spent in context switching, more so than on any given task. What you'll also notice is here, task 1 finishes in the 40th hour. It will take you 40 hours to complete any one of those 8-hour items. So you limit your work in progress. What actually happens? If we finish them one at a time, meaning that we only start one and finish it, then start the next one and finish it, it comes out to 32 hours. Now the math works. So what's another way that we can see WIP? And I'm kind of listing into cumulative flow diagram as a way of seeing WIP, but it actually shows us a bunch of stuff. So how many of you are familiar with cumulative flow diagrams and how they're used? All right, I got a handful of folks. That's good. So these things I think are super helpful for any team. They're relatively easy to create. So here's what we're going to do. Let's imagine we have a backlog. It doesn't matter what's in this backlog. What matters is there's these states: ready to start, in progress, in testing, ready for approval, deployed. I don't know if that's what it looks like for your team. That's what it looked like for this team. Fine. So what you do is each day you record the number of items in each of those lanes. You can sum up the points if that's what you're doing. It doesn't matter. I just count the cards. But either way, how much is in each of those lanes, and I just put it into a spreadsheet, and then I highlight all those numbers and say, give me a stacked area graph, and it gives me a thing that looks like this. That's kind of cool. Now, how do I read this? So, first, we can actually see how much is done and how much is not done. We can also see the work in progress at any given time. I'm counting in progress from the moment that the team picks it up to actually work on it in progress to completion of approval. Right? So I consider testing and the approval wait state to be part of the progress state. It isn't done until it's actually deployed. You may have, your mileage may vary, you may look at different things. Okay? I can also see the lead time, average lead time of a story. So this is the time from, hey, wouldn't it be nice if, to, hey, ain't that nice? I can also see the cycle time. So from the moment that we picked up the story to the moment that it was ready for approval. So how long was our actual dev and testing? And by the way, each of these states can have its own cycle time. So you can look at all of these various cycle times. And I can see scope change. So this one diagram tells me a bunch of stuff about this team. I know now, if you ask me for something today that wasn't even in the backlog, or you prioritize it from somewhere in the heart of the backlog to the top of the backlog, roughly how long it's going to take before it's done. When's that going to be done? Well, according to our cumulative flow diagram, it will be done on this date because it takes us this long to finish an average story. I also can see things like, maybe dev and testing isn't the problem when my lead time looks like it's about 16 weeks, but my dev time looks like it's about 2. Right? I can see a bunch of stuff from this. So just to give you, kind of drive this home and give you a better idea of it, I think you remember this diagram? We saw this earlier, right? This is the team that had variable velocity, and we couldn't say anything about them. We could make guesses. Same team, exact same data from this other perspective. Here's their cumulative flow diagram. This is literally the exact same data. What can you tell me about this team if you take a look at this for a bit? Yeah. There is a bottleneck in approval, absolutely. Their lead time is so long because stuff just sits here and builds up in approval, and then all of a sudden it all gets approved. And notice what else happens. All of this stuff gets approved. What happens to scope? It also goes up, right? Their product owner is a traveling salesperson. This individual's on the road almost all of the time, actually dealing directly with their clientele, showing them the product, talking to them, getting information from them. That's a fantastic thing. Except when they're on the road, they're super busy and they don't have time to do things like look at new software features that haven't been released yet. So when they get back into the office, then they plow through everything and they also go, oh, by the way, while I was on the road, here's a bunch of other stuff they need. That doesn't work so well. In fact, right here we can see that the team completely ran out of work to do. And so we gave them work before we approved the stuff that had already been done. But these can be super helpful for finding bottlenecks, figuring out what's going on, and helping you get to root cause, right? These can be helpful for just understanding that you might think that the problem is in testing. Testing takes us so long. And when you look at it, it turns out, whoa, wait a minute, deployment takes us really long. All right, so one of the things that we use velocity for is forecasting, or at least we try to use it for that, right? Yesterday's weather, whatever, my velocity last iteration was 27, so we're going to load the team to 32 this one, and we're going to cram it down their throat and make sure they make commitments, and then we're going to shame them for not, sorry, I may be a little jaded. But we use velocity for forecasting, sort of. We sort of forecast with velocity. What do we actually do? right? A lot of times what we do is something along these lines. We've got some kind of a target that we need to hit. We're looking at kind of how we burn up towards that target. We'll do some sort of, average, and we'll project a line up, and we'll go, okay, right there, that's the spot. We'll be done at exactly this point in time. Can you commit to that? Well, can you commit to those? How do you feel comfortable committing to those? The question is this technique accurate? Never. They're not accurate. We rarely, if ever, come close to actually hitting that target, right? Are they definite? No, they're not definite. If someone said, can you definitely hit that date? Can you definitely deliver on time? What's your answer? Oh, I don't know. Maybe? Are they even probable? Can you say, I don't know, probably? I'd probably hit that date. Cool. How probable? How probable? Well, how do we get to probable? Turns out there is a way to do this. We need a few things. We need our velocity. Hey, we got that. We need our backlog size. We probably got that too. These are the components we normally start with, right? Backlog size, velocity, do some division, time comes out. Okay, but there's other factors. When's the work going to start? Or when did it start? And what's our split rate? Split rate. Yeah. You got these stories in your backlog, and the odds are that by the time they play out, this one is going to turn into 2 or 3. That happens a lot, right? Progressive elaboration type stuff. We learn as we go. So what's your average split rate? If you know these things, you can actually run a probabilistic forecast using Monte Carlo simulation. Now that sounds really complicated, but lucky for us, the folks over at Focused Objective have created a way to do this. They've got resources and tools that allows you to actually plug this stuff in. So I'm going to show this real quick. Here we go. I've never done this before in my life in a demo. Boom. Okay. So let's say that we're starting today. Let's say that we know the number of items in our backlog, and it's 30. And so we're not giving a guess there. Now, our split rate, we think, is somewhere around 25%. For every 4 stories in the backlog, we get an additional 1. So I'm going to say the split rate is between 1, meaning nothing ever splits, and 1.25, meaning 25%. Our iterations, our velocity or throughput is based on 1-week iterations. We're going to use an estimate of velocity. We're going to look at the last 3 weeks. Let's just say that our velocity was 6 on the low and 10 on the high. And they want to know if we can get this work done by Christmas. Now, hopefully we're not delivering on Christmas Day, but it turns out with those numbers running through this tool. Now, what this tool has done is it's taken this data and it has run 500 simulations against this data, and then it has actually graphed probabilistically when would you get this stuff done. So it's showing us that it's a fairly wide range. We've got between a 35% probability and 90% probability of hitting 1225. So that feels like it's pretty good. We can say with some good level of confidence, yes, we can probably get that done. I've done this with a number of clients. Oftentimes what ends up happening is we come back and say, the range is wider, and we'll say, actually, we've got a 35% probability of getting it done by that date. But I've got an 85% probability of hitting the very next 2 weeks or 1 month or whatever is important to your business cycle. And very often when they know that, they go, okay, we'll wait till January. Right? But it's a good conversation to be able to have. And no longer having this, I actually brought this into a meeting and said, we have 85% probability, and the manager said, okay, but how confident are you? I need 100% confidence in your 85% probability. I'm like, go take a statistics class, dude. All right, I got one last point that I want to make real quick, and then I'll let you get out of here. Metrics are not for managers, or more accurately, they're not just for managers. Metrics are for teams. All of this data should be funneling back to the team. The team should be the one making the decisions about how they approach their work, what they need to do, how they're going to move forward, if they can or cannot meet a particular deadline, target, etc. That's all I have. Thank you. If you want more information, you can send a blank email to omblay@sendyourslides.com, subject line escape velocity. You'll get this slide deck along with a bunch of the research and materials behind it.